In this video, we're going to look at the combined gas law and how we can use it to do calculations when three characteristics of the gas are changing. So the combined gas law comes from combining Boyle's law, Charles's law, and Gay-Lussac's law into one equation. So this is the combined gas law. So PI/VI over TI is equal to PF/VF over TF. So we can now use this equation when all three variables are changing. Whereas when we were using any of the other three laws, the third variable had to stay constant. So when we used Boyle's law, temperature had to stay constant. When we used Charles's law, pressure had to stay constant. And when we used Gay-Lussac's law, the volume had to stay constant. So now all three can change. So let's look at an example. Sandra's having a birthday party on a mild winter's day. The weather changes and a higher pressure, 103.0 kilopascals, cold front, minus 25 degrees Celsius, rushes into town. The original air temperature was negative 2 degrees Celsius and the pressure was 100.8 kilopascals. What will happen to the volume of the 4.2 liter balloons that were tied to the front of the house? So we'll list our givens. We have an initial pressure of 100.8, an initial temperature of negative 2 degrees Celsius, an initial volume of 4.2 liters, and then the weather change. So we have a final pressure of 103.0 kilopascals, a final temperature of negative 25 degrees Celsius, and we need to find the final volume. So we check our units. Our pressures are both in kilopascals, so that's good. We just need to convert our temperatures to Kelvin by adding 273 to each of them. So there we have our initial temperature of 271 Kelvin and our final temperature of 248 Kelvin. So we start with the combined gas law. So there are multiple different ways that you can do the algebra to solve the combined gas law and the other laws for that matter. You may want to rearrange the equation to begin with, which is what I'm going to do in the next example. Or you put your numbers in right now and then you isolate your unknown. So for this one, that's what I'm going to do. I'm going to put in all my values where they belong and then leaving the final volume as my unknown. Okay, so then, and again, even at this point, there's a lot of ways you can do this math, right? You could do one side, you could do the multiplication division, you could divide the other side and then solve. So whatever works for you, you just got to solve for VF. So one way to do it, I'm going to multiply both sides by 248 to get rid of that 248 that's attached to the VF. Okay, so that cancels on that side. The Kelvin units cancel on the other side. Then I'm going to do some of that math there. So the 248 times 100.8 times 4.2 divided by 271. And so I have 387.429 and those 2 units left, kilopascal liters. And then the other side I've got VF and 103 kilopascals. Now I'm going to divide both sides by 103 kilopascals. Unit cancels and we're left with liters, which is what we were trying to find. So when you do that math, you get that the final volume of the balloons goes down to 3.8 liters. Here's a second sample problem. A 650 milliliter sample of nitrogen gas is kept at 875 millimeters mercury and 22 degrees Celsius. A change in temperature causes the nitrogen to expand to a volume of 850 milliliters and a pressure of 0.95 atmospheres. So what was the final temperature in degrees Celsius? So again, we'll write down our givens. We've got an initial pressure of 875 millimeters mercury, an initial temperature of 22 degrees Celsius, and an initial volume of 650 milliliters. a final pressure of 0.95 atmospheres. We're trying to find that final temperature in degrees Celsius, and we have the final volume of 850 milliliters. So we're going to check our units. Our volumes are both the same unit, so those are good. Pressures are not the same unit, so we're going to need to either convert the initial pressure to atmospheres or convert the final pressure to millimeters mercury. So I'm going to do that second conversion. So if I convert atmospheres to millimeters mercury, I get that this is equal to 722 millimeters mercury. So now that they're in the same unit, we can put them in the equation. And then we need to also change our initial temperature to Kelvin by adding 273. So now that we've done all that, we've got our units straightened out, we can use the equation Pi Vi over Ti equals Pf Vf over Tf. So this time I'm going to rearrange the equation before I plug the numbers in. So to do that, I'm going to cross multiply the temperatures to give me Pi Vi times Tf equals Pf Vf times Ti. And since I'm trying to find Tf, I'm going to divide both sides by Pi Vi, which will cancel them off on that side, and we're left with an equation for Tf equal to Pf Vf Ti over Pi Vi. And then, now that the equation is all rearranged, you just need to plug in all the numbers. So there we go. The millimeters mercury unit cancels, the milliliters cancel, and we're left with Kelvin, which is a temperature, so that's good. So when you put 722 times 850 times 295 divided by 875 and divided by 650, you get a final temperature of 318.3 Kelvin. We want to convert that back to degrees Celsius. So we're going to subtract 273 and find that the final temperature was 45 degrees Celsius. So those are some examples of how you can use the combined gas law to solve problems where all three conditions, volume, pressure, and temperature, change.